Okay, so let's start. So hi everyone. Thanks for being here. Sorry for not being with you there, but unfortunately to my knee injury, I couldn't make it. So sorry for that. So today I would like to talk to you about ZIO-Actors. So for the last few months, I've been involved in contributing to ZIO ecosystem, concretely to ZIO Core, ZIO-NIO, and ZIO-Actors. And for ZIO-Actors, I've completed actor system functionality and remoting. And I've given a talk about it during the functional Scala in London last December. And today I would like to show you pretty much based on that presentation, another talk about what's currently in ZIO-Actors. So let's start. So first, let's look into the agenda. So first, I will shortly cover the actors outline, so about the general concept. Then I will move to Akka to recall it quickly in just 2 slides. Then I will move to ZIO-Actors to show library design together with some examples, and we will see the differences and similarities with Akka. And the last part, I would like to share with you the problems you have to face while implementing your own actor system. So let's start. So about actors, so generally the concept of actor model was first described by Carl Hewitt in his paper from 1970s, where he defined the actor model as a set of actors communicating with each other that do not share a common state. And while reading this paper, we can recognize the features that we're currently using in, for example, Akka, like that we can delegate work to the other actors, so spawn actors, send messages to them, and delegate work to them. Also, we can spot their described interaction pattern, concretely the fire and forget, where we send a message and we do not expect a message to be sent back. So for the sake of the simplicity, let's simplify our actor system, actor model to such diagrams. So for us, actors will receive messages, and actor can process the message with a given manner. And within processing the message, actor can send finite amount of messages and spawn finite amount of children actors. And after processing the message, actor can update its behavior and continue processing the next message from the mailbox. So that was the general concept. Now let's cover what we expect from the library API, library design. So for us, actors should have a defined message type. So we should be aware what kind of messages we can send to an actor. Actors should have a known error type, so we should be aware what kind of failures the actor might fail with. Actors should form a supervision trees, so upon an error, we should be able to define some recovery policy for recovering from the failure. And actors should be, of course, location transparent. So we should not be aware whether the actor that we are communicating with resides on a local node or a remote one. So let's quickly, in just 2 slides, see Akka actors once again. So as you know, Akka contains the main module, the core actor functionality, so Akka Untyped, right now called Akka Classic, where we have where we can define actors, where we have to provide implementation for a receive method to define the behavior, the way of processing the messages. We have access to the actor system for governing over a set of actors that we will create. We can spawn actors and communicate with them. There is also a typed actors. So in that case, we can define behaviors with a behavior with provided type parameter for the messages that we can send to an actor. And with behaviors, we can easily update the the way we process the message after processing each message. Akka also provides multiple interaction patterns. So first highlighted snippet is taken from the docs, where we can interact in a fire and forget interaction pattern by the exclamation mark here. So we make no pre-assumptions that the message will be sent back to us. And there is also ask interaction patterns, so request response, where we expect a message to be sent back explicitly. And there are many, many more. In Akka, we have also remoting, widely used, and the remoting stayed within the untyped actors, but we can of course also use it with the typed actors if we want, by the actor refs proxies that are available. Okay, so that was the quick recall of the Akka. Now let's move to the actual ZIO actors. So first I will shortly introduce the ZIO. So ZIO is an effect type inspired by Haskell IO monad. And the ZIO project is a whole ecosystem containing multiple libraries backed by ZIO. For example, ZIO streams or ZIO test and many more. And here's the ZIO is the ZIO data type, which represents an effectful computations with 3 type parameters, where the first type parameter R stands for the environment that we have to provide to execute the effect, so for managing dependencies. Second type parameter is for the failures that the effect might fail with. And the last one, the A, is the type parameter for the possible success in case the effect completes successfully. Of course, there are multiple type aliases that we can use. So it makes it easier to avoid providing always all the 3 type parameters. So for example, an effect that needs no requirements and can't fail is a UIO. There is also, for example, task, which can by default might fail with a throttle, and there are few more. So let's move to the ZIO actors. So the first thing that we have available is, of course, constructor for actor system. So it's similar to Akka. And for constructing an actor system, we have to provide a name for actor system and optional config file if we don't want to use the default application conf. Having instantiated actor system, we have access to multiple methods. So make for spawning new actors, where we have to provide a unique name within the actor system, some supervision strategy, some initial state for the actor, and the stateful, so a description of the actor's behavior. We have also 4 type parameters: R for the environment, S for the initial state of the actor, E for possible errors, and F for the messages that we can send to an actor. There is also a select for a local and remote lookup, and the shutdown for stopping the whole actor system together with its all actors. So let's introduce the stateful. So for stateful, we have to provide the implementation for the receive method. So how we process the messages. And for receive, within receive, we have access to a current actor state, to a message that we're currently processing, and the context. So the handler to the actor system that this actor belongs to for actor lookup and spawning children actors. And here you can see the A type parameter within the receive, which is used for defining a type for a message that will be sent back to a sender in case of ask interaction pattern. So here in ZIO-Actors, we can define within the domain of the messages that we can send to an actor, also the messages that will be sent back in case of a ask interaction pattern. And processing each message must end with an effect, where effect must either fail with E or produce a tuple with a new state that will be updated, the actor with this state, and the message that will be sent back to a sender in case of ask interaction pattern. We have also access to an actor ref after instantiating an actor. So with actor ref, it's similar to the Akka. We can perform interactions. So question mark for ask interaction pattern, exclamation mark for fire and forget interaction pattern, and path, so access to actor's path. So we've seen the general design of a library. Now let's look into the few examples of the usage of this library. So let's see a simple example how it's typed. So imagine we want to create a simple counter, actor that behaves as a counter. So we define a message trait with a possible messages that we can send. So a reset for setting counter to 0, increase to increase it by 1, and get for retrieving the counter's value. And you can see in the brackets the types of messages that will be sent back in case of ask interaction pattern. So the first two are basically expected to be used as a fire and forget, and the get provides us with int, so the actual value of a counter. So let's create a simple stateful. So we create new stateful, provide the type parameters, so in for a counter, actor can fail, and the message trait that we created for messages. And then we provide the implementation for a receive method. All we have to do is pattern match on the message that we received and act accordingly. So reset set to 0, increase, and get is just returning the actual state. And all of this creates us a handler that we'll be using. So let's create a simple actor. So as it's taken from the test suite, we have first to create an actor system with some name. Then we can spawn a new actor, providing unique actor name, supervision strategy, initial state, and the handler that we created. Then we perform a chain of interaction operations. So we send the messages, and then at the end, we can check whether it acted as we expected. So basically, the fire and forget is asynchronous, as we do not wait for the recipient to process the message, but it's synchronous to the level of acquiring the information that the message was enqueued in recipient's mailbox. So by the moment we send the get, we already know that the two increase methods were already enqueued in a mailbox. So we've seen a basic example. Now let's look how to create a also simple finite state machine with this API. So imagine we have a such finite state machine, as simple as can be, with two states. And as you can see, this finite state machine isn't total, because there is no cell transition for a closed state. So for that case, we will fail an actor. So first, let's define our domain. First, we create a trait for commands that we can send to an actor. So open, close cell. And for cell, here's also string in case for using ask interaction. So for example, we send back some receipt or invoice. Then we create a trait for a possible state, so opened or closed. And then we create some custom case class for sales exception that I've described it earlier. So let's build a stateful for that. So we provide the types that we created earlier. And all we have to do is also provide receive implementation. And in that case, all we have to do is pattern match on the state that we're currently in, and then pattern match on the message that we received. So it's as simple as can be. So the first part regarding the open state. So for open is idempotent operation, nothing happens. For close, we can do also some logging, for example. And for cell, we do not change state, but we provide some message that we possibly can send back. In the closed case, it's pretty much the same, except for the cell message. And you can see that with ZIO, we can easily fail processing a message. Here's with IO fail, and provide it with a case class that we created that will be returned as an error in that case. So we've seen a basic example how to create with this API finite state machine and how to fail an actor. Now let's look at the supervision strategies. So the supervision, we can use it, is mostly provided by ZIO. So ZIO provides us with a set of the comprehensive and composable schedules that we can use for rerunning the effects. So now the small example from the test suite for testing some schedule. So here the important lines are 4 and 5. So we create a policy by supervisors retry and provide the ZIO schedule. It's about recurring given number of retries, and the test was about checking whether the schedule behaved as expected. And building schedule is easy. The ZIO provides us with an exponential backoff schedule, recurse schedule, Fibonacci, and we can compose them. So the last line shows us how to compose two schedules with a logical end. So such schedule will rerun the effect only if all of the schedule's requirements are satisfied. So this will recur 10 times with a span between the rerun in an exponential manner. So the last part I want to talk about is remoting support. So remoting support will be in future used for clustering functionality that we have in our backlog. So remoting is provided by ZIO config. So there's a great ZIO config built by AFSI within the ZIO ecosystem. And the configuration is pretty much the same as in Akka. For a remote, we have to provide a host name and port. And after providing the configuration, the usage is pretty much the same. We can create actor system, spawn an actor, and then on another node, we can perform a remote lookup by providing the absolute path to that actor on a remote node, and then we can perform the communication with an actor as its location transparent. So that was the general design of an ZIO actors together with some examples. Now I would like to share with you about the issues you have to face while implementing your own actor system. And while doing this, I was looking a lot at the Akka implementation, Akka source code. And the fun part of it was that I encountered such message in some source file that I might encounter dragons in the source code, which was pretty intense. So the first part I would like to talk about is serialization. So the end user can define the messages as they can be. So the case classes trait, they can be serialized as they are. The problem arises when we put in a protocol part of the actor system itself, because we can't serialize actor as they are, because after deserializing, the actor won't be able to communicate with its original host. So for that purpose, we have actor ref, and behind the actor ref, we have either local actor ref or a remote actor ref. So this picture from the docs describes this mechanism. So sending an actor ref via the wire is going to be deserialized in such manner that the deserialized actor ref will be able to communicate with its original actor via socket communication. So basically, once the actor goes through the wire, it becomes a remote one. And how we've done that? For the current version, we're using Java serialization for current proof of concept, early stage. So the serialized form of an actor is just path to that actor. So this is what is sent over the wire, path to the actor. So when deserialized, actor is deserialized into the remote actor ref. And when we perform interaction with remote actor ref, it will use socket communication to communicate with its original host. Java serialization is known to be slow and prone to attacks. So of course we have in backlog plan for providing another way for handling this. It's going to be probably covered in a separate project that we're currently working on, so the ZIO codex, that will be used also in other ZIO projects, not only ZIO-Actors, but also ZIO-Keeper and ZIO-Analytics. The second issue I would like to talk about is socket handling. So imagine we have multiple actors within a system that communicate with remote nodes, performing multiple interactions, fire and forget and ask patterns. And due to that issue, we will have to manage multiple connections. And for that purpose, we decide to use non-blocking I/O, concretely the Java-NIO. Thanks to the Java-NIO, we are able to utilize multiple connections with just few threads. We can do this thanks to the so-called selector mechanism. So the selector makes it possible to utilize multiple channels with just one or a few threads. So when the channel waits on an I/O operation, for example, because it's ask interaction pattern, the selector might decide to move the thread to another channel where the data is available for reading and writing. And we didn't need to implement it with a bare Java serialization, with a plain Java-NIO, because there is a great ZIO-NIO wrapper for that purpose. So at the end, I would also cover the goals we have for current year. So right now we are working on a persistence for ZIO-Actors. So it's pretty much the same as in Akka persistence for possibility of the event sourcing with a multiple data stores. In our backlog, there is also serialization, which I already explained. There is also plan for doing the monitoring, some telemetry for the actors. And the last one, so the one that people mostly ask about, so the clustering functionality. And we're going to archive it with a ZIO keeper. So you can also check out the process of arising the ZIO keeper. There is a great talk by Dejan Milic and Przemysław Wierzbicki from Functional Scala in London, where they showed what they've achieved by now in ZIO keeper. Okay, so I think that's all what I wanted to say. Thank you once again for listening. Sorry for not being with you. And do you have any questions?
Can you come closer to the microphone?
So can you hear me?
Yeah, sure.
Okay, because you said when I send a message, for example, using tel, it's done when the message is being enqueued on the receiver's queue or mailbox. Is that correct?
Yeah, sure.
And does it also hold for remote actors?
Yes, yes. For remote actors, it will also wait for acknowledge that the message was enqueued.
So you basically guarantee delivery of message.
Yes, delivery, yes.
Because that's not how Akka works, right? Akka doesn't deliver.
Yes, there are some differences, of course, but that's the way it's handled here.
And aren't you, well, won't it be a bottleneck? Because you don't always want to have this guarantee that the message will be delivered. For example, when you report some logs or some statistics every second, you can lose some of them, but you don't want to, and you don't always sacrifice performance for this guarantee. Yeah,
sure. We're going to see how it's going to, I guess, evolve. The core idea of ZIO-Actors was moved from the Scalac, actually. So when I started working with it, this core mechanism of handling the messages already there. It was already there. So I think it was originally implemented, part of it by John DeGauss. And to be honest, I don't know how it's going to evolve. So we're going to see that. We have plans for doing the benchmarks also. So we're going to see that.
Okay, thanks. I was just surprised hearing that you guarantee delivery, but thanks.
More questions? Okay, thank you very much.